Assalamu alaikum everyone. I'm Dr. Kamrul Islam presenting our work on neural implicit Islam pipeline tailored for real-time UAV inspection in dynamic aviation settings. Our goal is simple but demanding: accurate localization and dense mapping at flight speed on embedded hardware amid moving vehicles and challenging light. Civil aviation inspection demand continuous, reliable, and detailed simultaneous awareness. We need a real-time 3D mapping and localization to enhance safety, cut downtime, and enable predictive maintenance without grounding operations or overloading onboard compute. Our system, DM and SLAM UAV, fuses a dynamic object front end with neural implicit map and an efficient octree back end. The result is a SLAM pipeline that remains stable despite movers reconstruct dense surfaces for inspection and run onboard in real time. Here, the headlines of our they have a gain of 37.6% reduction in ATE, 23.4% better reconstruction completeness, 42% faster mapping than strong baselines, and 48 millisecond per frame latency on Jets and Orion. There are no offline members, they are achieved during actual flight. SLAM is the backbone of autonomous inspection. It provides precise pose estimates and dense geometry. For surface analysis, feature-based and dense methods have matured, but dynamic outdoor close-range inspection, runways, and aircraft still pushes beyond traditional assumptions. Four issues dominate: moving obstacles, vehicle personnel, non-rigid motion, flags, cables, rapid viewpoints, changes due to flight dynamics, and illumination variation outdoors. Each can destabilize tracking and blur reconstruction if not explicitly handled. Dynaslam or DSLAM mask movers to stabilize pose, but yield reconstruction that are too sparse for detailed inspection. IMAP singles MLP struggles with fine structure in complex scenes. NiSLAM assumes static indoor setting and is too heavy for real-time onboard flight. No price system jointly delivers robust dynamic handling to real-time dense mapping and embedded efficiency for UAVs. That missing combination is what motivated DMN SLAM UAV. First, a dynamic front and that segments movers online. Second, a multi-MLP implicit map stored in an incremental octree for fast sparse update. Third, a dataset and evaluation at scale showing 42.7 drift drop versus single MLP baseline 20.8 Hz on board with P less than 0.01 night frames. Now, related work. Now we have some classical SLAM. We use early approaches by using geometrical method like monoslam, PTAF SLAM, filtering sparse features. Later considered ORB SLAM as classical approaches. Then we are using dense method. In dense method like LSD SLAM and features extraction or GBD SLAM, they are using kinetic fusion, elastic fusions, and they have higher compute cost and depth requirement limit applicability. Now, we have seen learning-based VO bring depth flow priors, neural implicit maps like IMAP, encode scenes with MLPs, hierarchical latent grids like NiceSlam, improve detail, still most assume static worlds. Dynamics remain Achilles heels. Now, in our pipeline, we have three asynchronous threads: over synchronized RGBD, a dynamic front end to detect movers, post estimation for robust tracking and neural map back end for fast multi-scale surface updates using an I octree. Now, we use ULO V8 Nano to flag likely movers, people, vehicle or service cars, and validate motion with sparse LK optical flow against camera ego motion. The fused result is a clean binary mask empty that keeps static regions and filter dynamic pixels. Now, we extract ORB features only where empty is equal to 1 to avoid contamination from movers. PNP RONSEC seed is refined via direct photometric alignment against our current neural map rendering, while G2O optimizes the local pose graph. Now, space is partitioned by an incremental octree. Leaf nodes store 32D latent codes. 5 compact MLP decoders predict occupancy and color at progressively finer scales. We update only leaves intersecting the live keyframe frustum, achieving O-log and behavior. We jointly optimize camera poses X and map parameters O naught. The loss blinds photometric and geometric terms from neural rendering ITDT with accommodating inertial loop constraints and lambda is equal to alpha is equal to 1 and copies of the map consistently. Now, a base decoder F naught provides coarse occupancy color and higher level decoders add residuals delta O, delta C at final scale. This residual pathways capture both broad structure and subtle surface details for inspection. Now, we use Gauss Newton for pose, Adam for the map alternating updates per keyframes to maintain stability. Bounded complexity is enforced by updating only visible leaf latent codes, keeping compute predictable. Now, in our algorithm, we are using timing per frame, dynamic front end 6 millisecond for ULO V8 Nano, 3 millisecond LK 2 milliseconds, and something like post 8 millisecond keyframe. That maintenance is needed and map optimization of around 35 milliseconds. These pieces together to hit the real time targets. Now, in we are using a dataset composition. We use 20 real world airport sequences for the height of 5 to 30 meters, duration around 1 to 3 minutes, and they are synchronized with RGBD real sense D455 cameras of 640 to 480 resolution at 30 hertz, and we are covering the service traffic and airport fuelage or orbits for comprehensive evaluation. Now, we supply identical sensor input to all methods, aligning trajectory to ground truth using Haas method, evaluate mapping on static only structure to avoid bias from movers, and run paired t-test. Improvements are significant at p is less than 0.01. Now we have a quantitative results. DMN SLAM consistently achieve the lowest ATA score sequences compared to classical and neural baselines. Importantly, it does so while preserving dense surface quality needed for inspection tests. Now, this is a performance table against ORB Slam, Third, Dynaslam, and NiSlam. Our method leads an ATE, RPE, trans, and rotational errors and completeness while maintaining 48 milliseconds per frame time. The combination of accuracy, density, and speed is what set this work apart. Now, where ORB Slam Third produces 1200 sparse points, often polluted by movers like forklift, our method yields a continuous surface over fuselage, wings, nose curvature, engines, even petite tubes, while correctly filtering the forklift. Now this is a comparison table. Qualitatively, the classical pipeline shows scattered points and gaps that hinders anomaly detection. Our reconstruction is contiguous and inspection ready. Precisely the fidelity maintainers need for surface damage assessment. Now, on Jetson Neo, we sustain 20.8 Hz, nice slam runs 14.6 Hz, and our average latency remains around 48 milliseconds per frame. Operation during flight, not just offline processing. Now, in trajectory plots, the blue line ours closely tracks background truth, including segments with moving vehicles and personnel. Thus, that stability feeds directly into better, cleaner maps and safer autonomous inspection behaviors. Now, three highlights. A novel SLAM algorithm that integrates learned dynamic mask into neural mapping, nearly 37% ADE reduction, a multi-scale MLP plus octree design that improves completeness is nearly equal to 23% while cutting update time and DAAIS dataset with validated onboard performance. Now, we are exploring some mapping, proning for large-scale coverage, strategies for long-term airport monitoring, and further scalability to push beyond hundreds of meters without sacrificing real-time constraints. Now, conclusion. To conclude this, our DMN SLAM or UAV fuses dynamic segmentation with multi-MLP neural implicit map to deliver accurate, dense, real-time inspection on embedded hardware. We report significant improvement in trajectory error and reconstruction quality, and we release code, DIS, and pertinent model to support the community. If